Good. Well, this is, believe it or not, the last in my series of lectures on shaping modern mathematics of this year. It has gone past so quickly. It just shows you how time flies when you're having fun. And the last one, I'm going to talk about applied mathematics or mathematical physics, or what in the 18th or the 19th century used to be called mixed mathematics. And that's the mathematics used to investigate the physical world. And Britain, in the Victorian era, was preeminent in these investigations. Let me start the overview of the lecture by talking briefly about the situation at the end of the 18th century. In the 18th century, many master mathematicians, such as Laplace and Lagrange, had built on Newtonian mechanics to describe and predict the motion of bodies on the Earth and in the sky. They had the underlying equations for the motion of bodies. Indeed, they had them in various formulations, and they investigated these equations mathematically. But the behaviour of heat, light, electricity, and magnetism had yet to yield their governing equations. And this lecture is about applying mathematics to these four areas of heat, light, electricity, and magnetism. I'm going to start with Joseph Fourier, the distinguished French mathematician, physicist, Egyptologist, demographer, and public servant, who tackled the conduction of heat and found the fundamental equations of the conduction of heat, as well as finding new mathematical methods for solving those equations. Then we will look at the work and lives of four Victorian mathematicians: George Stokes, William Thompson, later Lord Kelvin, Peter Guthrie Tait, and James Clerk Maxwell. They were collaborators and friends, and together changed the face of mathematical physics. I will pick out Stokes' work on water waves, which still raises important unsolved research questions today. Thompson and Tait produced a very important textbook on mathematical physics, which placed the conservation of energy at the heart of its approach. First time that was done. Thompson also made use of Fourier's technique in very important work on tide prediction, and that's going to be the first of my two case studies. And I'm going to finish with the most important of them all, James Clerk Maxwell, because of his work on light, magnetism, and electricity, and that will form my second case study. Joseph Fourier worked on what are now known as Fourier series. I'll describe what they are shortly. And this led to many of the most important mathematical discoveries of the 19th century and had major applications in mathematical physics. Fourier was born in Burgundy and in 1797 succeeded Lagrange in the chair of analysis and mechanics at the École Polytechnique in Paris, leaving the following year to join Napoleon's invasion of Egypt as a scientific advisor. On his return, he was appointed by Napoleon to an administrative position at Grenoble in southeastern France, organising the draining of swamps and supervising the building of the road across the Alps from Grenoble to Turin. In his spare time, he carried out his important mathematical research on the conduction of heat, which he published in 1822. The excerpts on this slide are from his 1822 Analytic Theory of Heat, and the left-hand side is the title page of the original, and on the right-hand side I've got some extracts from the contents pages of a subsequent translation. Fourier wrote, "Fundamental causes are not known to us, but they are subject to simple and constant laws, which one can discover by observation and whose study is the object of natural philosophy." I want to pick out three things that Fourier achieved. First, he derived the fundamental equation for the conduction of heat and the resulting temperature distribution. And on the slide, on the bottom right, you might be able just to make out at the bottom of the page the heat equation in 3 dimensions. I'm going to look at it in a moment in 1 dimension and pick out some of its key features. Then, he developed the marvellous and powerful technique of representing a function or a waveform in terms of trigonometric functions. We just need to know how much of each trigonometric function to throw into the mix. And I'm going to see a practical example of that in Kelvin work on tide prediction. But first, the heat equation. I thought I would use this nice drawing attributed to Bombieri, the famous mathematician, of Fourier's cellar, as a concrete example of an application of the heat equation. So what we have is the problem of trying to find out the distribution of temperature as we go vertically down into the Earth through a few meters. And we're going to describe the temperature by the symbol U. U of x comma t is the temperature at depth x at time t. So it's a function of two variables. X tells you how far you are down, t tells you what time you're at it. Now, the crucial thing seems to me is that you don't write down an equation explicitly involving the temperature at depth x at time t. You look and see how the temperature is changing. And there are two ways that the temperature can change. At a particular point, it can change in time. And for a particular time, the temperature can change as you go up and down. It changes with position. So let's look at the left-hand side of the equation at the top, the du by dt. That's just telling us the change in the temperature at a particular time. But you're already saying to me, Raymond, that will be given by the amount of heat flowing into the point or the amount of heat flowing out of it. That's the only way the temperature can change in time. So how do you find the amount of heat flowing in or the amount of heat flowing out? Well, that's going to depend upon the temperature gradient as you go down through the Earth. And the temperature gradient is given by du by dx. It's given by the change in temperature as you go down. And what is the change of the temperature gradient? Well, that turns out just to be the second derivative. So that equation is saying, on the left-hand side, the change in temperature with respect to time is given by the amount of heat flowing into or flowing out of the point. And K is going to be a constant of proportionality, which is going to depend upon the material of which the Earth is made, the makeup of the soil, and so on and so forth. So that was the first thing that Fourier did, was to develop an equation giving you the temperature. And what we have to do now is to solve that equation to obtain the temperature at point x at time t, knowing what the energy, what the sunlight is, how the temperature is varying on the surface of the Earth. That will be a given thing that we will come to in a moment. So that's the first thing he did, the derivation of that equation. I took you through it very quickly, but I think hopefully from what I've said, you can see it's not quite as intimidating as it might have looked at first sight. The next thing he did that was crucial was a way of looking at various functions that would arise. And I'm going to illustrate it with an example that Fourier used of a square waveform. And the square waveform is the blue line on this diagram. It's a waveform that oscillates between two values, a positive value and an equal negative value, and it does it in a regular fashion. And it's also still very important in digital electronics and digital engineering, where something oscillates between +1, -1, or whatever. And what I want to do is follow Fourier's footsteps and show you how that can be approximated more and more exactly by a sum of trigonometric terms. And on the screen, you see the first of those, which is just simply the cosine of u. Fourier had a technique of calculating what the terms would be in this approximating Fourier series, and I will try to illustrate this when we'll come along to Thompson's work on tide prediction. But the next term using Fourier techniques is cosine of u minus a third cosine of 3u. He had a way of calculating what the coefficients were, and what I've done now in the red graph is to superimpose the first two terms of the Fourier series. And you can see that it's getting closer to the blue curve. The first three terms of the Fourier series, the coefficients are 1 of cosine u minus a third cosine of 3u plus a fifth of cosine of 5u. And when you look at it, it's getting better. we're able to look at successive approximations, and I only did the fourth one because there was no more room on the slide, thankfully. Cosine of u minus a third cosine of 3u plus a fifth cosine of 5u minus a seventh cosine of 7u, and I bet you can see what the pattern is. And if you continue that on to infinity, you obtain an approximation to the square wave curve that would be in the handout for you at when you pick that up at the end of the lecture. Well, in fact, it's in the handout even now. Good, so we're able to, therefore, be able to approximate this waveform by a trigonometric series. And the crucial thing, really, well, he wrote about this here. He said it was a very surprising outcome. It is necessary to examine them with care and to interpret them in their true sense. And you'll see one of the difficulties there, in that what's happening is when the waveform jumps from +1 to -1, the Fourier series converges, in fact, to the average of those two values. So, in fact, converges to 0. But that's in the handout. He then went on to consider the question of which functions could be represented by Fourier series in this way. He also derived formulas involving integrals for the coefficients, involving integration, summation for the coefficients of the Fourier series. And in fact, the question of what conditions should be imposed on a function so as to ensure its Fourier series does in fact converge to the original function generated much new mathematical activity. Now, it said there were three things that Fourier made use of, and the third one is one of great power as well, and it's the concept of linearity. We are very fortunate, or nature seems to be constructed in a way, that many of the equations describing the behaviour of natural phenomena are linear. Now, what that means is that if you can find, by hook or by crook, some way, two solutions, two different solutions, then in fact you have a whole lot of other solutions. The sum of those two is the solution. The difference of those two is the solution. Twice the first one plus once the second one is the solution. In fact, if alpha and beta are any constants, alpha times the first solution plus beta times the second is a solution. That is a great simplification, and you can begin to see perhaps how it may relate to the idea of Fourier series, where you break something down as a sum of trigonometric terms. Right. And there's one example that I think is particularly useful, and it's to do with linearity of water waves on the surface of a pond. And quite an amazing thing happens. It's very relaxing as well. For example, if you throw a stone into the pond, it's going to generate some waves. It's going to generate some ripples. And I come along and I throw a stone into the pond at a different point. I will generate waves and I will generate ripples. And you will see that the ripples that I've generated will behave as if the ripples that you generated weren't there. They will pass through each other as though the other were not present. So the result of you throwing the stone into the pond, let's say, is U1. That gives you the wave pattern. The result of me throwing it into the pond is U2. If I were just to do it my own, both of us to do it, the result is U1 plus U2. That's what I mean by linearity. Well, what Fourier did in order to find the temperature distribution down to the cellar was that he wrote the solution he wanted to find, U, in terms of a Fourier series. He also wrote the temperature distribution at the surface due to the sun coming out, due to the passing of the year, as another distribution in terms of the Fourier series. And as a result of that, he was able to find what the solution was at all different times, at all different points on the way down. And what he found, for example, was that about 4.5 meters down, depending on the value of K, the temperature fluctuates very little over the course of the year. And of course, this must have been known empirically for a long period of time. People didn't wait for Fourier to come along to decide when they were going to build their cellars and how deep they were going to have it. But of course, it could be applied in many other situations where you're heating a body and you're keeping certain parts of the body at certain temperatures and you want to find what the temperature is throughout the body. So I just chose that as one example, partly because he did so and partly because it's the one-dimensional, but it captures the idea. And to say the idea being that you look for the solution in terms of a Fourier series, in terms of trigonometric terms. Right. And Fourier's work, as we'll go on to see, is very influential on mathematical physics in the 19th century. and in particular what I call Victorian mathematical physics. So let's turn to the reign of Victoria. The Victorian era was characterised by the dominance of Great Britain, both militarily and economically. It lasted from 1837 to 1901. It was the age of Peel and Palmerston, Gladstone and Disraeli, Tennyson and Thackeray, Dickens and Wilde, Stanley and Livingston, Gilbert and Sullivan. It was the age of the Great Exhibition, the Crimean War, the Suez Canal, the Indian Mutiny, and the American Civil War. It was characterised by industrialisation and rapid urban growth, far-reaching social and political reforms, vast colonial expansion overseas, and impressive scientific developments. Increased urbanisation resulted in Britain moving from being a primarily agrarian to a largely industrial society. Parliamentary reforms enfranchised whole new sections of the population. Innovations such as the telegraph and the railways revolutionised daily life, while Darwin's theory of evolution challenged the very basis of people's beliefs. And an area of which 19th century British mathematics could be uniformly proud was applied mathematics, where new techniques were used on a large range of problems. And here I show 4 of the main players. I've clearly had to leave some out. William Thompson, later Lord Kelvin. Peter Guthrie Tait, George Stokes, and James Clerk Maxwell. They succeeded enormously in applying mathematics to understanding the physical world. They worked in many areas: mechanics, thermodynamics, electricity, magnetism, hydrodynamics, and the theory of gases. George Gabriel Stokes made major contributions in the area of hydrodynamics, elasticity, gravity, light, sound, heat, solar physics and chemistry, and his name is remembered in mathematical physics for Stokes' theorem and the Navier-Stokes equations describing fluid flow. And the Navier-Stokes equation forms the basis of one of the Clay Millennium Prizes, and I introduced you to one of these in my lecture earlier on the Riemann hypothesis, giving you a chance to win £1 million and give you a second chance to win £1 million. Because as the Clay Mathematical Insight, the Clay Institute website describes it, waves follow our boat as we meander across the lake, and turbulent air currents follow our flight in a modern jet. Mathematicians and physicists believe that an explanation for and prediction of both the breeze and the turbulence can be found through an understanding of solutions to the Navier-Stokes equation. Although these equations were written down in the 19th century, our understanding of them remains minimal. The challenge is to make substantial progress towards a mathematical theory which will unlock the secrets hidden in the Navier-Stokes equations. Now, Stokes was born in County Sligo, Ireland, and attended schools in Dublin and Bristol before entering Pembroke College, Cambridge. He graduated as senior wrangler, that is, gaining top marks in the final examination in 1841, and became Cambridge's Lucasian Professor of Mathematics in 1849. During the long tenure of this position, for over 50 years, he restored the reputation of the Lucasian chair to the high point it had when occupied by Isaac Newton. And in later years, Stokes explained why he took up the study of hydrodynamics. I thought I would try my hand at original research, and this is quite a good prescription if you're thinking of original research, and following a suggestion made to me by Mr. Hopkins, a famous Cambridge tutor, while reading for my degree, I took up the subject of hydrodynamics, then at rather a low ebb in the general reading of the place. And he went on to say at a meeting of the British Association for the Advancement of Science, when he reported on hydrodynamics, that the fundamental hypothesis on which the science of hydrostatics is based may be considered to be that the mutual action of two adjacent portions of a fluid at rest is normal, perpendicular to the surface which separates them. He took this as his underlying hypothesis, not only for hydrostatics, but also for hydrodynamics. After 1850, however, his output of academic publications slowed. This was mainly due to his involvement in academic administration. For example, he became Physical Sciences Secretary of the Royal Society, but also to the time and effort that he spent in corresponding with colleagues. He was exceptionally supportive. He encouraged them, he commented on their work, and he communicated their results. Well, Stokes had a nearly 60-year friendship with the next person I want to talk about, William Thompson. Thompson, later known as Lord Kelvin, he was a dominant figure in Victorian science, with contributions to mathematics, to physics, to engineering, particularly in the areas of electricity and magnetism. He was a leading figure in the creation of thermodynamics, the area concerned with heat and energy, and was instrumental in laying the first transatlantic telegraph cable. Thompson was also born in Ireland. He was born in Belfast. He was educated at Glasgow and Cambridge universities and was appointed Professor of Natural Philosophy at Glasgow University at the age of 22. He remained at Glasgow until his death and was buried in Westminster Abbey alongside Isaac Newton. Peter Guthrie Tait on the right, not somebody you might want to meet in a dark alley at night, carried out research on a wide range of topics: quaternion theory, knot theory, atmospheric and meteorological phenomena, thermodynamics, aerodynamics and kinetic theory, as well as the colouring of maps. He was born in Scotland, Dalkeith, educated at Edinburgh and Cambridge universities, became Professor of Mathematics in Queen's College, Belfast in 1854, so I think he was 23, and took up the chair of Natural Philosophy at Edinburgh in 1860, which he then held for more than 40 years. He collaborated with Thompson and also with James Clerk, Maxwell, the last person I'll speak about, as well as William Rowan Hamilton, a distinguished Irish mathematician and mathematical physicist. Well, I just want to draw out what essentially was the start of the modern approach to mathematical physics that arose on a textbook that Thompson and Tait worked on, a highly influential book called The Treatise of Natural Philosophy, physics, mathematical physics, and so on. And they started work in 1861, and the next little bit I put in for any of you that happen to be working in collaboration with somebody to produce a book. It proved to be highly influential in identifying and putting at the centre the idea of conservation of energy. And although it fell far short in scope from its original author's intentions, but what books don't, it was very influential. Now, the two collaborators had very different nature. Thompson frequently went travelling, while Tait didn't leave Scotland after 1875. Tait also was very argumentative, for example, over the relative merits of vectors and quaternions. But it was Tait who drove the collaboration towards publication, berating, cajoling, and coaxing Thompson to keep to deadlines. Tait's frustration is illustrated in a letter he wrote to Thompson in June 1864, about halfway through the collaboration. I am getting quite sick of the great book. If you send only scraps and these at rare intervals, what can I do? You've not given me even a hint as to what you want done in our present chapter about statics of liquids and gases. And he continued, there was a more practical concern. I have the kinetics of a particle almost ready, nearly the whole of the next chapter. But I don't see the fun of paying 30 shillings for sending the manuscript to you in Germany for revision, when all probability you won't look at it to some indefinite period when you're in Arran, where it could be certain of reaching you, and for 8 pence. Well, Thompson and Tait had three main purposes for the project that resulted in the treatise. They were to provide appropriate and affordable textbooks to back up their lectures. They thought that people were being ripped off by the textbooks that were being produced in London, and they wanted reasonable ones for their Scottish students. They wanted to nurture physical intuition and mitigate against relying on mathematical manipulation. And what has survived, the other points have survived as well, in a pedagogical sense, of course, but the underpinning educational philosophy, to base their natural philosophy on the conservation of energy and extremum principles, replacing Newton's principia of force with a new principia of energy and extrema. And the treatise was very well received. I don't have time to go into the details of what they did, but it's still a very modern approach. And James Clerk Maxwell, for example, his view of Thompson and Tait's achievement was that the two northern wizards were the first who, without compunction or dread, uttered in their mother tongue the true and proper names of those dynamical concepts which the magicians of old were wont to invoke only by the aid of muttered symbols and inarticulate equations. And now the feeblest amongst us can repeat the words of power and take part in dynamical discussions, which, but a few years ago, we should have left for our betters. Maxwell was also quite a good poet, and I think you can see that in that passage. Now, the second edition of Thompson and Tait features a marvellous discussion on continuous calculating machines, bringing together previous work by Thompson and his brother James. There are machines, when you look at this, quite amazing, things rolling over each other and against each other to solve simultaneous equations, to integrate the product of two given functions, to find the solution of linear second-order differential equations with variable coefficients. But the one I wished to use for illustration was the machine for predicting tides, which computed the depth of water over a period of years for any port for which the tidal constituents have been found from the harmonic analysis of tide gauge observations, Fourier series. You see how well this lecture is constructed with the coherence and the repetition. That is, from the coefficients of the Fourier series representing the rise and fall. And in fact, modern tidal analysis and prediction in all its mathematical and mechanical detail is due to William Thompson from around 1867. And in his lifetime, Thompson was seen as the most important natural philosopher of the Victorian age. But the waxing and waning of the 20th century and the supplanting of classical physics by relativity and by quantum mechanics have eroded his reputation, so that for many people he's remembered as little more than a unit of temperature, the degree Kelvin. And it was Thompson who used the phrase substituting brass for brain when discussing the mechanisation of tidal prediction. That's a lovely, I think, image of him shortly after graduating at Cambridge in 1845. So what I want to do briefly is to go to the next slide. Show how to describe the tide. Introduce the beautiful idea that allows us to calculate the tide theoretically, and illustrate the practical developments that allow us to calculate the tide practically. But I want to start and end this section with two invasions separated by 2,000 years, to illustrate how important it is to know in advance about the behaviour of the tide. My first invasion is Caesar invading Britain, and the other one will be the D-Day landing in Normandy during the Second World War. This is what happened to Julius Caesar when he invaded England in 55 BC. That night happened to be the night of a full moon, when the Atlantic has the highest tides, and we did not know this. So the longships, which had been pulled up on the beach, were swamped, while the supply ships, moored to anchors, were tossed about by the storm. Many of the ships were broken up, and the expedition was cut short by this disaster. Now, the tide is caused by the pull, the gravitational pull of the sun and of the moon on the oceans, and also the rotation of the earth. But its exact pattern at any particular spot on the coast depends on the shape of the coastline and the profile of the sea floor underneath. So even though the forces that move the tide are completely understood, the tide at any one spot is essentially impossible to calculate theoretically. What we can do is record the height of the tide at that spot over a certain period of time and use those measurements to predict the tide at that spot in the future. And I want to show you how that can be done. Now, the tidal force is governed by a small number of astronomical motions, which are themselves periodic. But the various frequencies of their periodicities don't have a whole number ratio, so that the whole configuration never exactly repeats itself. There's an almost exact 19-year cycle in the joint pattern of the equinoxes and the solstices and phases of the moon. So the tidal record repeats itself almost exactly if you wait long enough, 19 years. And this fact had been used to prepare tables for the European ports. But a major motivation for Kelvin's work in predicting the tides was India, where they did not want to wait 19 years for accurate tide predictions. Because the Earth, Moon and Sun are in relative motion, the gravitational pull at a point of the ocean is constantly changing. And the 5 main astronomical periodicities are the length of the year, the length of the day, the lunar month. And then you also have the fact that the axis of the moon's orbit wobbles. It's called precession. And also the plane in which the moon is moving, that also wobbles. It's called the rate of precession of the plane of the moon's orbits. But when you look at the geometry, you can see that the gravitational pull can be described using a collection of sine waves. And this for you is a collection of sine waves with increasing frequency as you go down. Of course, it could also be a collection of cosine waves, because the sine waves and cosine waves are just shifted along from each other. Right? And from the geometry of the situation, the geometry of the solar system at the pull and the point of a place in the ocean, one is able to say that the height of the tide at a given place is of this form. It's the sum of trigonometric terms plus another 120 similar terms, but there you are. Now, the point is, from the geometry, from the length of the day, from the length of the year, from the length of the lunar month, from knowing the rate of precession, and so on, we know what the frequencies are. Those V1, V2, V3, V4, they are multiples of the fundamental ones. So this applies to any point, right? What will be different from point to point is how much of the mix you have. What is the A0, the A1, the B1, the A2, the B2, the A3, the B3. That's what we need to find for each particular point. All right. And here we have an example of the tidal record in the River Clyde at the entrance to the Queen's Dock, Glasgow. And I think if you look on the left, you'll see there's 7. It's for 1 for each day. So this is the height of the tide at the River Clyde. So one can make those. In fact, Kelvin developed a tidal gauge that would automatically, the water going up, he would have a pen going around a cylinder that was rotating that would automatically create a graph like this, and this is one of them. He was really quite an amazing engineer. All right. Now, what we need to do is to use this record, as I say, it's for 7 days, one on top of the other. You can see how it's shifting along. To find what the coefficients are. And this is where it becomes even more pretty. Now, we don't want to do it for 120 terms. We don't want to do it for 12 terms. We're going to do it for 2 terms. We're going to have a pretend tidal record. And notice the cunning title, The French Connection, Fourier Analysis. On the left, we have got a tidal record. It's a pretend tidal record, but it is of the form so many times sine t plus so many times sine of the square root of t, square root of 2 times t. Right? It's just the sum of 2 terms. This is just to illustrate how we go about finding A and B. And that's what I've said there. In this curve, we know it's made up from sine t and sine square root of 2 times t. We don't know how much there is of each of these in the 2 trigonometric waves. We don't know the coefficients A and B. But if I go back to these sine waves, there's no horizontal axis put in, but if you put the horizontal axis for each of them in at the appropriate point, and you were to calculate the area underneath it as you go along, you would see that the long-term sum of the area is going to be 0. Because there's a bit above the axis and a bit below. a bit above, a bit below, a bit above, a bit below. So looking at the average area as you go along is going to be zero under a sine curve or under a cosine curve. Right. But let's see how we make use of that. We know it's of the form a sine t plus b sine the square root of 2 times t. So I'm going to take that expression, multiply it by sine t, and now I'm going to calculate the long-term average. What I have when I multiply by sine t is a times sine t times sine t. That's a times sine squared t. And then I've got another term, b times the square root of 2 times t and sine of t. Now, because those two frequencies are different there, I'm able to express that product of two sines as another trigonometric term, and I've just went back and tried to convince you that the long-term average under a sine or a cosine is going to be 0. So if I multiply by sine t and calculate the long-term average, the b term is going to drop out, and all I'm left with is the a term. And having done it once, I'm going to do it again. I'm going to multiply that expression now by the sine of the square root of 2 times t. And then the a term is going to drop out when you calculate the long-term average. And on the bottom, I've got the blue wave, which is the tidal record, and the red on top is calculating the long-term average and giving me a, and the term in green below is when I multiply by the other trigonometric term and calculating the long-term average and giving me the green term. So when you have a Fourier series, all of these trigonometric terms, you pick one of them, you multiply it by that one, calculate the long-term average, and the only thing that survives is the coefficient corresponding to the term that you multiplied by. Very powerful. And this is just what I've said. The method followed can be extended to the complete calculation. Take the series, take one of the terms, multiply by it, calculate the long-term average, and the only thing that survives is the coefficient of the term that you've multiplied by. And that gives a little more detail, which again will be in the handout. Okay. So let's go on and see how it was all put together. However, there was a lot of practical work in taking these two series, the tidal record that you had from your tidal gauge and the trigonometric series, and multiplying them together. And this was where William Thompson's brother James came in, because he was able to devise a mechanical apparatus for taking those two series, taking the tidal gauge record and taking the graph of the other trigonometric term and being able to mechanically multiply them together to find out what was the long-term average. So that with James's Thomson invention, what you could now, once you were given the tidal record, was you can find what was the composition of the coefficients at the particular point that you were interested in. So you now had the coefficients in the Fourier series. The matter now was to reverse it, put it all back together again, and that's what Thomson did with his tidal machine, which is here and is really quite beautiful. We have 15 pulleys, so you can count that while I'm talking. We have a wire which is fixed here, goes over that pulley, down this one, over the next one, up and down over the pulleys. We have a handle that you turn, that you crank, with different gears. It's connected to different gears along here. And those are so geared as to give the frequencies. I think this one just has the 15 frequencies. So the gears here give you the frequencies, and the arrangement is such that you put in the amplitudes that you obtained from the tidal record. So as you turn the handle, these gears go round, the pulleys go up and down, and at the far end here, it's only shown as a little weight, but what Thomson had was a pen attached here against a piece of paper which was moving, and it would move back and forth and would give you the predicted tide. So the two components that give rise to the tide were the frequencies, but the frequencies were set by having the gearing, and then how much these pulleys were allowed to move up and down, which was the amplitudes, and you got the amplitudes from the tidal record. And it worked up as far as 19 43, 44 at least, because if we look here, this is on the right, Kelvin's tide machine, overhauled 1942 to handle 26 tidal constituents, and one of the machines used by the Liverpool Tidal Institute to break tides for the Normandy invasion. So how to use it? If you wanted to use that for a particular machine, if you wanted to use that machine to find the tides at a particular point, you needed to send those coefficients through. And that's what's happening on the left-hand side. A most urgent note to Dudson from the Admiralty Superintendent of Tides, listing 11 pairs of the tidal harmonic constants for a location codenamed position Z. And they'd been obtained, I believe, by sending little submarines out there who were observing the rise and fall of the tide over a period of days in order to analyse to find out what the tidal constituents would be. They are the amplitudes that are given, and they are fed into the setting of the Kelvin's tide machine in order to predict what the subsequent behaviour of the tide is going to be. Okay. So finally then, let me turn to James Clerk Maxwell, the most important of the lot. So the left James with his mother Frances in about 1834. He was born in 1831. Not possibly the kind of photograph any of us would want put up, but and that his father about 1850. His mother and Maxwell both died young, in their late 40s. Well, Maxwell is widely considered to be one of the most important mathematical physicists of all time, after only Newton and Einstein. And foremost among his contributions to science was the formulation of the theory of electromagnetism, but also made major contributions to colour vision, I'll say a little bit about that, and optics, the kinetic theory of gases and thermodynamics, and the understanding of the dynamics and stability of Saturn's rings, which is where he first started to deal with a large assemblage of particles moving together, which he then used that experience in his work on the kinetic theory of gases. He was born in Edinburgh, entered the university there when he was 16. 1850, moved to Cambridge. 6 years later, returned to Scotland to the chair of natural philosophy at Marshall College in Aberdeen, where he was made redundant when the college was amalgamated into Aberdeen University. He was then professor at King's College London and first Cavendish Professor of Physics at the Cavendish Laboratory in Cambridge, where he was intimately involved in designing the laboratory and contributed to the purchase of its equipment. Well, while at Edinburgh, Maxwell was interested in colour vision, and it had been suggested by Thomas Young in 1800 that there were 3 sets of colour receptors in the eye. Maxwell and a colleague identified 3 primary colours as red, green and blue. But what he did was to quantify the mix of the 3 primary colours in order to obtain any other colour. And he did this by means of his colour top, which we can see there. On the top of the top, you have a way of being able to put down the red, green and blue in particular proportions by overlapping them. You could have a certain proportion of each of them. Then you wanted to match a particular colour. You put that particular colour in the centre of the disc, and you spun the disc until the 3 colours with persistence of vision gave the colour in the centre. You would adjust the proportions of the red, green and blue until you obtained the colour in the centre. So it wasn't qualitative. The essential thing about it was this quantitative way of obtaining what proportions of the primary underlying colours made up every other one. And of course, like any good lecturer, when giving a lecture, he'd been asked to lecture to the 1861 excuse me, to the Royal Institution on colour vision. He wanted to illustrate the lecture, but of course, quite hard with a little colour disc in order to be able to show that to the audience. But there was photography. Perhaps he could use photography to show the phenomenon to such a large audience. And it was possible to project a black and white photograph onto a screen, so it's large enough for the audience to see. And Maxwell wanted to see if he could make a colour photograph and project it in the same way, illustrating that any colour could be made up by mixing the three primaries of red, green and blue. For this, he would need to take 3 photographs of the same object through red, green and blue filters in turn, and then project them simultaneously on the screen through the same 3 filters, resulting in the first colour photograph of, naturally, a tartan ribbon. Now, it worked, but it shouldn't have. The result could not be duplicated. The problem was, it turned out, that the then available photographic plates were sensitive to light at the blue end of the spectrum, but much less to light at the red end. Maxwell had been lucky because of sensitivity of the emulsion to the ultraviolet. Instead of photographing the ribbon under red light, Maxwell was actually photographing it under ultraviolet light. So the mixture of colours which Maxwell obtained was ultraviolet, blue and blue-green, not the mixture red, blue and green he believed he had obtained. He had been lucky in obtaining his first colour photograph, but somebody like Maxwell tends to make their own luck. But Maxwell is mainly remembered, and this is what I will conclude with, his work on electromagnetism, which has truly changed the world. Now, he began his researches on electricity and magnetism shortly after graduating in 1854, and continued with them until shortly before his death, 1879. Now, it's a complicated story, and here I can only select some key features. I want to start with Ørsted's experiment on electricity and magnetism, and I think it's one of the most important of all experiments. What we have is that we have a current moving along the wire, which is what's being held between the 2 hands in the sketch. You've got an electric current moving along a wire, and it produces a force upon the magnet, which we can see down beneath it. And that pushes the magnet, swivels the magnet into the paper on the left-hand side and out of the paper on the right-hand side. I hope you can see that from the schematics of the diagram. There are 2 things in this experiment that I want you to take away. Unlike anything known before, it was caused by something in motion. It was caused by a current, by electricity in motion. Nothing up to then had been caused by something in motion. Things attracted each other, things repelled each other. Also, the force generated is not an attractive force. It's not a repulsive force. The wire isn't attracting the magnetic needle. It's pushing it at right angles to it. It's pushing it into the paper on one side and out of the paper on the other. And it was Michael Faraday who came up with a representation of that using his lines of force. And here we see Faraday image delivering a Christmas lecture, and there you see something that you may have done at school, unless it's now considered too dangerous, of putting a sheet of paper over a magnet and sprinkling it with iron filings, and you have these lines of magnetic force going out. So the electric current was generating circular lines of magnetic force around the wire, and that was causing the magnetic needle to go in and out. But a very different kind of behaviour from anything that had been seen before. Now, Faraday was an important influence on Maxwell, as indeed was Thompson. Thompson had developed a formal connection between the equations of electrostatics and the equations of the flow of heat. And in fact, Maxwell's first equation dealt with an analogy between lines of force and streamlines in an incompressible fluid. Then he started the development of a theory of electromagnetism, which made extensive use of Stokes' work, so a sense of community coming through there. Now, the paper that I want to talk about from Maxwell is the one in which he postulated a medium that would fill space and would account for the stresses associated by Faraday with his lines of magnetic force. And he concluded with the property that vibrations of this medium would have properties identical with life. So prepare yourself for something shocking. On the left-hand side, Maxwell's model of molecular vortices and electric particles. So everything is filled with this. And what we have is an array of hexagonal vortices in an incompressible fluid. So I think you can see lots of, there's a hexagon, there's another hexagonal, there's another hexagonal. And I can only have time to pull out some bits of it because in a sense, how can I put it? This is nonsense. Maxwell, the quote I'll show you in a moment, also says it's nonsense, but it was a very powerful engine of discovery. So he's going to say that the magnetic field is obtained by the hexagonal vortices rotating. And if you have got the hexagonal vortices rotating, you have something akin to the centrifugal force. Because the Earth is rotating, the Earth bulges out at the centre and contracts at the poles due to the rotational effect. So with these vortices rotating, they're going to expand out, and that's going to cause a ripple to move out sideways. Similarly, there's going to be an attraction vertically, so they're going to behave essentially qualitatively, in fact he does show quantitatively, in the same way as Faraday's magnetic lines of force. So to some extent that takes care of the magnetism. The magnetism is due to the rotating of the hexagonal vortices. But you may have noticed that, and it may have jarred with you, that if you have vortices rotating in the same sense, they're going to jar against each other. And that's why we have these little round particles, little spheres in between them, which act as idle wheels that engineers use when you have things moving in the same rotational sense in order to be able to allow them to do it. And they are the electrical particles. So the rotating vortices are the magnetic, give rise to the magnetic field. The little spheres give rise to the electric fields. And the third thing was that he supposed the medium to be elastic. And the thing about elastic things is that elastic things support waves. And he calculated what the speed of the wave motion. And he was able to do that in terms of the ratio between two electrical units, the ratio of the electromagnetic and the electrostatic units of electric charge. And it turned out to be the speed of light. And his quote, he then said, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." Now, Maxwell was unhappy, as indeed were many, or all, with this model of whirling cells and idle wheels. And he wrote, "The conception of a particle having its motion connected with that of a vortex by perfect rolling contact may appear somewhat awkward. I do not bring it forward as a mode of connection existing in nature, or even as that which I would willingly assent to as an electrical hypothesis. It is, however, a mode of connection which is mechanically conceivable and easily investigated. And it serves to bring out the actual mechanical connections between the known electromagnetic phenomena. So I venture to say that anyone who understands this provisional and temporary character of this hypothesis, will find himself rather helped than hindered by it in his search after the true interpretation of the phenomena." Well, it turned out that he was able to resolve this difficulty in a paper of 1865, where he provided a theoretical framework based on a few general dynamical principles for the propagation of electromagnetic waves through space. And Maxwell wrote about this paper quite charmingly, I think. "I also have a paper afloat containing an electromagnetic theory of light, which, till I am convinced of the contrary, I hold to be great guns." And in this paper, and in his treatise on electricity and magnetism, he developed Maxwell's equations. And Maxwell's equations in modern form are that, where you have B and H being the magnetic flux density and the magnetic field strength, and E is the electric field strength. And there's no whirling vortices, there's no idle waves, there's nothing like that at all. And it's impossible to stress just how important Maxwell's equations have been. They're immensely practically and theoretically important. And I want to finish with the assessment of two people of great standing as to the contribution that Maxwell has made. The first is Einstein, and the second is Richard Feynman, a distinguished physicist. It's interesting how you give the first name for Richard Feynman, but you don't give it for Einstein. And Einstein said, since Maxwell's time, physical reality has been thought of as represented by continuous fields and not capable of any mechanical interpretation. This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. Let me tell you what I thought Einstein meant, and I haven't said that very often, actually. In other words, Maxwell went from a mathematical description of a mechanical model involving vortices separated by rolling spheres to the complete abstraction given in his treatise on electricity and magnetism. Maxwell stripped away all the imagery of the model until finally all that remained was the mathematics. The mathematics was the model. This transformation was, possibly, James Clerk Maxwell's greatest achievement. And I'll finish, which I think is a fitting point to end a lecture on modelling the world, by what Richard Feynman predicted, a Nobel laureate. He said, from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. Thank you.